All right, guys, welcome to section 10.4 green theorem. Okay. How come I cannot type in? In this class, there are 4 theorems. Very important theorem. We learned one of them in the previous section. This is the second one. A curve that does not intersect itself. Anywhere between its endpoint. Okay. This is simple. And we get into a little bit into our topology here. This one, not simple. Okay. Another definition. A closed curve is the curve that ends at the same point where it begins. That end at the same point where it begins. Okay. Closed. Not closed. Then you can say that's not simple. Okay. Definition. A piecewise smooth curve is the smooth curve joined by multiple piecewise curves. It's a smooth curve joined by multiple piecewise curve. Piecewise smooth curve is something like this. See. À. Just do two of them. See, there's two of them. C1, C2. Or you can have it like this because this is the very useful piecewise smooth curve here. C1, C2, C3, C4. A closed curve that has a positive orientation has a positive orientation if it has a single counterclockwise traverse okay, so this is a curve that has the positive orientation here. Okay. And if you go the other way, this is the negative orientation. Okay. Yeah. Try to circle here so it look nice here. And I put a point here. Actually, let's put a point right here. Okay, we have all the definition here. So now here come the theorem, right? Here come the green theorem. Okay, what's the green theorem? Let me say that let's see be a positively. I just write out exactly what I say. Oriented piecewise smooth simple and closed curve in the plane let D be the region bounded by C. If PQ qxy. Have continuous partial derivative. On an open region that contains D. Then we have this one. Pxy dx plus q xy dy is equal to double integral over the region D q x minus py dA. Okay, let's look at the left side here. The left side. Well, what exactly is the left side here? You can actually do this to the left side. Pxy dx plus qxy dy, right? Well, this is pretty much the same as integration. I forgot to write the curve C here. Closed and bounded. PQ dot dx dy. You can do a little bit more. Let's see, PQ, you can think them at the vector field F, because this is the two components of the vector field. And then dot, what is this one? Dx dy, and you can rewrite this thing as dx over dt, dy over dt, dt. So what is this thing here? F dot, this is the tangent vector r prime t dt. So what is this? F dot dr. But in F dot dr, you have a circle here. So the left side is exactly the circulation. The circulation. Yeah. Okay. Now let's look at the right side. Well, what is the right side here? Qx minus py. It looks like we are summing a bunch of qx minus py, right? Over the region D. It's the summing. But then you can do a little bit more here, so you can see exactly what we are summing here. Qx is the partial derivative with respect to x up q minus partial derivative with respect to y up p. dA. And then this one, well, it does look like a determinant of some sort. It looks like this. Determinant of ij, partial x, partial y, pq, dA. Okay, for now, I won't go to the next section, but when we study the next section, this is what is called a micro circulation. This is the in section 16.5. What this is the once you get there, you understand what this is. This is the curl f of the vector field f dot k. dA. So curl f dot k is the micro circulation. We can think this as the micro circulation, or the component of the curl in the z direction. It's the sum of all the micro circulation. Inside D. The bigger circulation is equal to the sum of all the smaller circulation. That is the idea of the Green theorem. The proof is a little bit different. Some people use PQ, some use MN. I'm just going to put a note here. MN is more useful in differential equation. You will see this notation in when you take the differential equation. Focus on one integral. So focus on this one and show that this is the same as one of them. It doesn't matter which one. So here, if you work it out, you will see that one of them, this one and this one, they will be the same. So that is why in the proof, right, they say that they only work out one of them. It's the line integral m dx. So if you do m dx that on the left hand side, focus on the left hand side here. This one, m dx. You will see that well, look at the curve. So you have this is a rectangle, right? So you have bottom, top, and then the two sides. We don't sum the two the two vertical side because the dx, they are zero. So it's just the bottom and the top, right? So if you do the bottom, then well, you see that you have integration from a to b, and then on the top is, well, it's b to a. It's because of the you travel in the opposite direction. Once you work out the integration, right, Now you're gonna look at the double integral. So this is the second pocket. I'm gonna do the red marker so that you see it. MYDA. So you do this one. Work out the double integration, and then when you work it out, you say that, oh man, we come up with the same thing, exact same thing, right? So this one part of the proof. And you can actually verify this thing only for, you know, something very simple. Then you can actually verify the green theorem. It's not that bad though. Okay, so here come computer work done by the force field. D. Okay, so here come the force field. Sine root x plus 2y e to the negative y square plus 2xy in moving a particle along the curve C as below. If you choose to do directly, if you compute work directly, then work here, it would be integral along C1, C2, C3, C4, C1 f dot dr plus C2 f dot dr C3 f dot dr C4 f dot dr. Yeah. So that's what you would do, right? You can do it if you want to verify the green theorem. But then, you know, we don't have time. Yeah, we definitely don't have time to do this thing, which can be long and tedious. Okay. Notice that there is circulation. The curve C form region D. I would say enclose a region D. And C is simple and closed. Symbol closed. Sure. Okay. So we can use the green theorem. Right? Circulation is double integral over the region D, because we are summing a bunch of these smaller circulation, these micro circulation here. What are the micro circulation? Well, if you look at it, it look like the determinant of this matrix. As one of the best way to remember is remember the determinant of this thing. So it's going to be a partial x of the second one of the second component. Oh man, I don't have no room here, so minus partial y of the first component. Partial derivative with respect to x of e negative y plus 2xy minus the partial derivative with respect to y of sine root x plus 2y dA. Okay. So what do we have here? We have a, oh, amazingly, 2y minus 2. Well, you can set dA to be a dx dy or dy dx, up to you. It doesn't matter. Right? If we set dx dy, then x is go between 0 2, y go between 0 1. Right? So dx dy zero 1 0 2. Two y minus 2 dx dy. Evaluate this one. Oh man, with respect to x, that is gonna be a 2 0 to 1 2y minus 2 dy. And what do we have? We have a 2y squared minus 2y 0 1. So that is the 2 times 1 squared minus 1 times 2. So minus 2. If you look up here, hopefully you noticed why the answer is negative. The orientation of the curve C is mostly against the vector field.